Okay. So today is the first class, and the first class I teach usually binary search algorithm. We all have learned about this algorithm at certain part of our life, and we all have applied it. It's a very simple algorithm. It's like you have a set of data, and the only criteria you have to have in that data is that it is sorted. And based on that, if you want to find a key in that data, we figure out like where the key exists, whether the key exists, and if it exists, where it exists, right, in the data, right? So there are few things which we need to know about this algorithm is input. This is an array or a sorted set, right? And then there is a key, right, which we want to find, right? And most of the time we return an index, so because we already know the key, so there is no point returning the key. So index is the return value of the algorithm with the implementation, and index is the return value, and if you don't find the key, you return -1, right? That's the simple algorithm is okay. There is a sorted set. Instead of looking from one by one and going through all the elements in the set or array, which will take you O of n, because you will be comparing it with O of n times, right? Why don't you split the array into half, or you just check the key in the middle? If the key is in the middle, so let's say if this was my array, right? What you do is you check the middle, right? If middle is the key, we found the key and we just return, right? But if middle was not the key, then since the array is sorted, you know that all the elements on this side will be greater and all the elements on this side will be smaller than the mid, right? So based on the relationship between mid and key, you can actually decide where not to look or where to look, right? So if key is less than mid, right? If that is the case, does it make any sense to look for key into this side, right? No, because if this is a sorted array, right, then all the elements on this side have to be greater than mid. So the key will always be on this side, right? So what we'll do is we search in the left part, right? Now, if the other way around, if the key is greater than mid, then there is no point searching on this side because we already know that the key is less than all the elements on this side are less than the mid. And we search on the right part, right? This is the fundamental of binary search, right? You have a mid, you have a key, and you have a sorted array. Based on the relationship between mid and key, you either discard the right part or you discard the left part, and you just live with the other half, right? And then you do the same thing again on the smaller part, again on the smaller part, again on the smaller part. When do you stop, right? You stop when there is no element to be searched. That means there is an empty array. In empty array, your key cannot be there. You can be sure that in an empty array, your key doesn't exist. So you can easily return -1, right? If I give you an empty array and I say, hey, do you find a key in this array? What will be your obvious answer? Hey, it's not there, right? So we stop when array becomes empty. And this is important. We don't stop when array has one element. We stop when array becomes empty. Yeah, and I will tell you how to find that out. But let's start with basic implementation of binary search. We all have heard about this recursive binary search implementation, right? This is an integer array, an integer case. So this is Java code, but I don't think Python has anything different. This will be like this is an array and this is an integer, right? And then this is a return value. What we do is, um, and then of course we pass the integer start and integer end. So this is the most important piece of binary search, that we are not more concerned about A. We are concerned about S and E, because our recursion or our splitting of the array works on start and end, right? So upper bound and lower bound, and I'll tell you more importance of this as we go in the class, right? So what we do is, if S is less than E, what does that mean? If S is less than E, and this is where you have to pay attention, right? What is S and what is E? So S is always 0 and E is A dot length minus 1. Because why A dot length minus 1, right? A lot of people say like, why not A dot length, right? Because you want to return an index, right? A dot length is not a valid index in an array because it's outside of the index, right? Indexes are 0 to A dot length minus 1. And since you want to return an index, either you will return a start or end or mid, like which will be in between S and E, you have to have this range in a valid indexes. That is why S starts from 0 and E ends at A dot length minus 1, not A dot length, right? Now coming to this expression, which is this guy, right? Why S is less than E, what does that signify? Because this is very important. I will use this again and again and again in like 5-10 different binary search problems. But pay attention here, why S is less than equals to E, what does that mean, right? So let's start with a very basic array. If I have an array which is empty, I have a hard-coded start equals to 0. What will be the end? End will be A dot length minus 1. What is the A dot length here? Is 0 minus 1. What is the length? The end minus 1. In this case, your start is greater than end. In this case, your start is greater than end. That means the array is empty. So start greater than end represents array an empty array, right? Remember that start greater than end represents an empty array, right? Similarly, if I had an array of one element, what it will be? Start will again be 0, end will be length is 1 minus 1, which is 0. In this case, start is equals to end. In that case, it represents one element, right? It represents one element, right? If start is equals to end, it represents one element. If a start is greater than end, it's an empty array. And in case, let's say we take an array of two elements, then start is 0, end is 2 minus 1, 1. In this case, there are more than one element. If start is less than end, then there are more than one element. What I said, you have to stop when array is empty, right? So if start is less than end, that means you have more than one element, right? So you don't have to stop there. You have to stop when start is, sorry, in this case, it will be greater than end. If start is greater than end, we already know that it's an empty array, right? That's what we understood from here. If start is greater than end, it's an empty array. We don't need to search anything. Just return -1, right? That's it. Else, what will we do is we'll find the mid, which will be S plus E divided by 2, right? And then we'll do if A of mid is equals to key, right? If it is equals to key, you will return the index mid. Else, what will you do? You'll do if A of mid is less than key. That means the A of mid is less than key, then you have to go on the right hand side because key is greater. So you have to go on the right hand side. So you will just call the same function, binary search, again A, the key. Here your start will change. Start will go to mid plus 1 because mid till mid it cannot be possible, right? because it's greater than, right? And then you end remains the same, right? You return from here. If that is not the case, you just do the same thing with the start remains the start, but because you're looking into the left hand part, your end changes to mid minus 1. That's it, right? You can actually write this code in a different way where you can look at, hey, while if s is less than equals to e, right, then do this, right, whole of this thing, and then at the end return the -1. You can write any which way you want, right? Either you return from the start or you change the condition, return at the end, right? But this is the crux of binary search algorithm, right? How I find like whether it's s is less than equals to or s is less than or less than greater, all those things are here. I need to stop when there is 0 element in the array, empty array. That means I have to stop when start becomes greater than end, right? Or I do everything till the time start is less than or equals to end. Like the same thing said in two different ways, right? So this is the crux. There are two problems with this implementation, right? The first one is this one, right? This is an overflow problem. If you know this, what will happen if start or end is like very close to 2 raised to power 32, which is the integer size, right? If it becomes integer size, what will happen is if you add anything to it, right, it will overflow and it will circle back, right? And that will lead to infinite loops, and you'll see like, oh, nothing is happening because your s is never becoming greater than equal or greater than e, right? Because overflow happens. So let's say if you have a value of 2 raised to power 32 in index end, right, and then you add 1 to it, it will just go to negative 2 raised to power 32 minus 1 or something like that, right? So it will just go reverse, right? It will just overflow and then it will never get out of that loop or get out of that recursion, right? So that's the problem with that s plus e overflow conditions in huge sizes of the array, right? And the other thing is recursion itself, right? Recursion has implicit memory requirement, right? Implicit memory requirement means if you are using recursion, it uses stack, right? All the things which are not yet finished execution go into the stack, and then they pile up on the stack, right? More depth you go into the stack, into the recursion, more stack frames are on the stack. That means you're implicitly using that space. One thing you should always know is stack is more expensive than heap because it's smaller in size and it is allocated in a system memory rather than the heap, right? So it doesn't take a lot of depth of recursion to actually make a stack overflow, right? It's not heap, which is like big enough to actually deal with all our intricacies or mistakes of leaking the memory, right, for a long time. This will overflow within seconds, within 2 seconds, right? Because if you have an infinite recursion, it will just add stack frames, and that's why the stack overflow occurs, right? So there are inherently two problems with this: integer overflow and the recursion, which uses an additional memory, right? So how can we solve those problems, right? The first problem can be easily solved. It's just that you change the expression into this one: mid equals to s plus e minus this one. This will still give you the mid. You can check it. Like let's say if my start was 0 and my mid was 7, sorry, end was 7. So if I do this, it will be 0 plus 7 divided by 2, it will be 3, right? If I do this, it will be 0 plus 7 minus 0 divided by 2 equals to again 3, right? You can put any values and you'll see like this expression and this expression always give you the same result. But this expression, right, doesn't lead to overflow because we are not adding anything to the end, right? Here we are adding anything start to end, right, which may not be non-zero, which may be non-zero, and in e can be like 2 raised to power 32, and then it can overflow. But since we are not adding anything to the end, right, That's why the overflow doesn't occur. So change the mid integer mid expression to that expression and you are safe, right? Recursion, of course, we can do it iteratively, right? So that we save that extra memory which we are spending. So let's write iterative code and then I will start into problems, because once you get that code, it will be easy to like integer array A, integer key, right? And this is where we are going iterative, right? So for any binary search, we need start, which is 0, and end, which is a dot length, right? Now what we have to do, we have to do the search till there is at least one element in the array. That means till s is less than or equals to. If it is greater, we stop, right? So if I write a while loop, it should be s is less than or equals to. I will explain how to come up with this, right? But you know the basics, right? If s is greater than e, that means I have done everything, right? There is no more element to be searched. If s is less than or equals to end, that means there is at least one element to be searched. That's why I'm going to the while loop, right? In while loop, I do integer mid equals to s plus e minus s divided by 2, right? And then we go yep. So we check if a of mid is equals to key, right? Then return mid, right? If that is not the case, just check if a of mid is less than key, then you look into the right hand part, because a of mid is less than key, so the key should be on the right hand side. So your start changes, start goes to mid plus 1, right? Else your end changes and it becomes mid minus 1. If you never return from this, right, you never return from this statement and you are having an empty array now, so you can be sure that you will not find it. So you can just return -1. That's it. That's a simple non-recursive or iterative implementation of binary search. So it doesn't use the stack, right? So we save that memory and it doesn't overflow, right? And it's simple to debug. It's simple to understand, like, start and right, everything. And this condition is most important because this is where we almost every time fail, right? Hey, whether it should be s less than equals to, right? So remember, binary search algorithm continues, the vanilla binary search algorithm continues till there is an empty array. If there is an empty array, you can safely return -1. So you have to run the while loop till the time you have at least one element in the array. And one element means start is less than or equals to end. That's why it is s is less than equals to end, right? Cool. So this is the vanilla binary search, right? I spent so much time on this because now we'll be solving problem after problem after problem, which will be slight variation of this particular search, right? And we'll be able to solve those problems, right? Any questions till now?
What would be the complexity of this one, the
I will
vanilla?
cover it. I will cover it
Okay.
after time complexity class, because if I tell you it will be log of n, it doesn't make any sense, right? So we'll come back to binary search algorithm class once we cover the master theorem, right?
Okay. Can you one more time repeat why recursion was not good? Like, I understand it uses stack implementation, but why was it not good?
Because it uses stack implementation, right? It
Yeah, but
uses
why
implicit
is a
memory
stack implementation not good?
because it's extra memory. So see, do you see any extra memory used in iterative version?
No.
Then it's bad, right, to use an extra memory.
Okay, got it.
right? So that's the whole reason that recursive is not bad. I would not term it as a bad. It's like just an extra memory which is being used there, and it has a dangerous a path. If you forget something here and there, you can actually do a stack overflow which can crash the entire system, right?
Got it.
Here you can't do that. You can go into infinite loop, right? If your conditions are not correct, but you're not consuming system memory anywhere, right?
Okay, and how are we handling a scenario where key is not found at all?
We are returning -1, right?
So it will still search for the entire loop, even though that key doesn't exist.
How would you know without searching?
Got it.
Yeah. How would you know that the key doesn't exist, right? Without searching into the array. And it's not entire, right? It's log of n. That's why the beauty of binary search is that you discard the half of the array with one comparison, right? So it's not, we are not searching the entire array, by the way, right? Otherwise the linear search would have been done, right? If you have to search for entire array, a linear search is okay, right? Here we are
Okay,
not
clear.
searching the entire array, and without searching the array we can't say that key doesn't exist, and that is
In
why.
one condition we can say that, right? For
Mhm.
example, this is a sorted array, so if the key basically greater than the end of the end element, last element of the array, or key less than the that, in one condition we can prevent.
Yes,
uh,
extra code,
yeah,
right?
yeah,
So I would restrain you from not doing that. You know why? Like I see the value of that, what you just said. The problem is whenever you add extra code, it doesn't mean that you write two codes, two conditions there and then it works. You have to write test cases for them, right? And that means those conditions have to be covered in your test cases. So there is an extra code, so there is an extra test case, right? And never write any extra line of code if it can be handled in a generic way, right? And then you're not saving anything in the complexity part as well, right? In a worst case, complexity is still O of log n. It's just the very specific cases which you're testing, right?
that's
So
correct.
yeah, I would like I heard this somewhere, which is a good code is the code where you can't add anything, you know, but a great code is the code where you can't take out anything. It's the bare minimum which is required to work the solve the problem. That's the great code, right? You can add any conditions, any extra code and make it work for specific cases faster, but it is a maintenance nightmare, it is a test case nightmare, and then refactoring nightmare, right? So it's not that you are getting away with writing this function and nobody will look at it, right?
Yeah,
So
but actually, sir, what it's like I remember. So very recently, I've gone through with Amazon coding,
Mhm.
like interview. So I remember. So after the telephonic round, the very first round, like he gave me a problem on array,
Mhm.
and then when I skip this this condition, like whether array is of greater than zero size, and like these things, which eventually like also can covered by the for loop, right? Because if I'm running a loop and I'm also checking a length, eventually it's gonna cover. So
Yep.
like those conditions they expect, like even those are the smaller conditions, sometimes they expect to run before you actually write your main algorithm.
Yes.
So yeah.
Yeah. Go ahead. Go ahead.
Yeah, that's what I'm trying to say. It's like so in those cases, like he eventually mentioned this to me, that you are not checking this condition. So
Yeah.
when do we decide that we should do that? When we do decide that we should not do that?
Yes. So let me ask you one more question in the depth, right? What were you doing in the for loop, or were you accessing the first element before the for loop?
No, 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 not at
Right.
all.
Then it was a wrong thing for him to ask, right? So it's
Mhm.
not that interview tells something it's the right thing, but yeah, sometimes people have say their own, like, hey, I would like to do like that, right? But if your code was not accessing the first element before entering into the for loop, why would you check for the length? Right? Because the for loop itself checks for the length, right? It's a redundant code,
That's true. Yeah.
right? So it doesn't make it right just because an interview said it. I understand your feeling, but if you were accessing something into the array before entering the for loop, yes, that would have been a necessary step, right? If you look at a lot of lead code problems, right, where you have two dimension array, right? And
Mhm.
we look at, hey, rows equals to let's say board dot length, and columns equals to board of zero, board of zero. Let me write it, then it will be more clear. But good question, right? So a lot of time we do this, hey, I have in a two dimension array, which is C, and we want to find, hey, how many rows are there? So we do like, hey, C dot length, which is correct. And then we do column equals to C of zero dot length, right? This is where you have to do that. Hey, if C dot length is greater than zero, then only you can access it, right?
Yeah,
I
that's true.
understand that. Sometimes in dynamic programming questions, we do that, right? Hey, let's say LIS of zero is, let's say, A of zero, right? This is where you have to check if the array dot length is greater than equals to or greater than zero, right? Because you are accessing the index. If you're not accessing the index before starting the for loop, it's not necessary, right? And coming back to the specific of a case of binary search, it's not necessary at all. It will eventually get it right. Then you are like, the problem with that kind of code is like you are coding like if I give you if and else, you can code anything, right? With if and else, you don't need for loop, you don't need anything, you just if and else, if and else, if and else, you can do that. So more if and else you put in your code, more test cases you have to write, right? So if ever the person asks you to do that, and if you are not convinced, right, just raise this reasoning with him, like, hey, I have to write another test case for making this work, right? This, at least this condition work. Because nowadays companies are very peculiar about statement coverage and branch coverage on their automated tests, right? So if you write an extra code, you have to write an extra test case to actually cover that condition, whereas the same test case would have covered the entire code, right? Other test cases. Anyhow, it's like sometimes there is a peculiarity around interviews, but yeah, you can reason it out. If it doesn't understand, just put it there. Yeah.
Yeah.
There is no harm done. Actually, the code doesn't become wrong, but it's just that it's a vestigial code, doesn't use anything. Yeah. Anyhow, let's go. So let's take one small problem on binary search first and then go from there, right? You must have all heard about this problem, which is finding the first instance of an integer, of a number in a sorted array. Have you heard about this problem? So there are duplicates. So let's say if there is an array like this, this is sorted array, but there are duplicates in this sorted array, and we want to find the first instance of the key. So if I give you key equals to 3, the first instance is this, right? If I give you key as 7, the first instance is this, right? So we had to find the first instance of a,
Sorry, sir.
sorry, you're saying something?
Yeah, sir, I have to ask something. So in the earlier case, we didn't have. Yeah, yeah. Are you not able to hear?
Speak. Speak. No, I can't hear you, Rajat. No, even if you had duplicates, it was any case you would have returned. So if you had duplicates in the earlier case in a binary search, you would have written any index which finds the key. In this case, you want specifically the first instance, right? So that's the difference of the question. Have you heard about these questions earlier?
No, I haven't actually. I mean, I have like not exactly this question, but like more or less a little bit different, like finding the number of like duplicates number for each, like how many times they occur.
Yep. That I will bring that question in 5 minutes. Let's that's a very like this is a flow which will go there. But let's start with the first instance and we'll end up there, right? And you'll see like how easy it is to find that, right? So let's start with finding the first instance, right? It's a sorted array. The first thing which is sorted array you should think is, hey, maybe there is a scope of binary search. But in binary search, right, whenever we do mid, right? So yeah, there is a tip. Whenever you are dealing with an array problem, right, always 110%, right, indexes on top of it. It helps you so much, right? Because you don't have to keep your memory, keep this data in memory, right? So yeah, there was a very good seminar I attended about how our brain works, right? And the guy said, right, our brain is good for long-term memories. It's more of a hard disk, right? Not for a processing of the data in a short term, right? No, sorry, it's good for processing the data, but not storing the data for the short term. It's good for storing the data for long term, good for processing the data, but it's not good for storing the data for short term, right? So if you start storing these indexes in your mind, your brain has like your memory is running out, you know, the RAM is running out. You have a lot of hard disk, right? So don't make your brain remember these numbers. It's a psychology thing, right? Just write it down. It will make your life so easy, right? While you are doing the calculations. Sometimes we just try to store everything in our brain for the calculation even, right? So anyhow, trivia. Let's start with the binary search implementation. What happens, right? Our mid will be this, and in binary search implementation, what we used to do is, if a of mid is equals to key, we'll return it, right? But in this case, that will be wrong, right? Because this is the last instance, actually, not the first instance, right? So how can we modify the binary search algorithm to return us the first instance, right? So what do we know if a of mid is less than, sorry, is equals to key, key we are looking for? What do we know from this, right? We know that this instance can be the first instance. We are not sure that it is the first instance, but it can be because it's equals to key, so it may or may not be the first instance. But what we are sure of is anything beyond it, right? If there was 5 threes after this as well, let's say there were 3 3 3 3 3 and then 4 5 7, none of these 3 3 3 3 will be the first instance because we already have one before it, right? Getting my point? Since we already have a of mid equals to the key, nothing after it will be the first instance. We don't know about this instance, like it may or may not be, maybe there is other instances before it, but nothing after it will be the first instance. We can be sure of that. Do you agree with that?
Yes.
Yes. So what can we do now? We can discard anything after the mid, right? But mid cannot be discarded, right? So we have to, because mid may be the case, right? But if mid was, let's say this was more of like 4, right? In this case, mid is greater than the key, right? In that case, we can even discard mid, right? Because yeah, 4, if 4 is the mid, then neither this mid nor anything after it can be the first instance of 3, right? It has to be on the left hand side. right? So this is the crux of the algorithm. If a of mid is less than if equals to key, right, you don't discard the mid, but you reduce the array, right? If it is greater than the a of mid is greater than the key, you discard the entire array, you go mid minus one, right? What if this key was, let's say, 1 2 let's say 3 3 4 4 5 6, right? And we are looking for the first instance of 4, right? In this case, mid will be here, right? And then a of mid is less than the key we are searching for. That means you have to discard the entire left hand part, right? Because the key cannot be, the first instance of the key cannot be on the left hand side. So there are 3 cases, right? Let's write down them one by one. If a of mid is equals to the key, that means that this a of mid can be the first instance, or something before mid will be the first instance. So your end becomes equals to mid, because mid cannot be discarded. Mid is still a candidate for the first instance. That's what I meant, right? If a of mid is less than key, hey, this is the case. If a of mid is less than key, you the the first instance cannot be on the left hand side, it has to be on the right hand side. So your starts becomes mid plus 1, right? And if a of mid is greater than key, right, then your your first instance cannot be on the right hand side, it has to be left hand side. So you change the end equals to, right? That's it. When do you stop?
When E is less than S.
E is less than S. Why? E is less than S. That means you have an empty array.
Yeah, less than or equal to.
Less than and equals to, that means you have one element into array, right? So if S is less than or equals to E, that means there is at least one element in the array, right? If S is less than or equals to E, there is one element in the array. What if that is the key? Because if you stop there, what if that particular number, which is only one element in the array, is actually the key? There are 2 possibilities, right? Either that number is not the key, or this number is the key. So how do you work out that specific case, right? Because you just can't, like in this specific case, you just can't go till empty array, right? You have to stop when there is one element array, because I will tell you in the test cases, but let's understand this, right? You have to stop when there is one element. In vanilla binary search, you stop when there is an empty array, right? Because you can, in this case, you can easily make the condition at the last, saying that if there is only one element, right? And this is where your Prabhay comes into picture. If there is one element, I will just check if this is a key. If it is a key, this will be the first instance I will be returning. If that is not the key and there is only one element, I'll just return, right? That there is no key, there is -1, right? This we can do, right? And I will tell you why the other empty array generic conditions will not work. Let's implement it, and then we'll see like why generic condition will not work, and we have to put a specific condition for that case. So let's write this code the same way I wrote the thing, integer first instance.
Yeah, can you go back to the first earlier page? I have a question there.
Yep.
Yes, so here, since we have a repeated number just before 3, it will get stuck on the first one itself, right? So how would it move?
Oh, sorry.
Because the mid of the key will be still equal, right? So E equal to mid.
Equals to mid, yes.
So how would the the cursor move to that it has to move on the left hand side or the right hand side?
Let's take an example and see how it moves. So let's say we had this array, right? Right? Have you ever dry ran a binary search? Let's do that, right? So what is our S? 0. What is our E? 7. Yeah, that's the thing. Okay,
Yeah.
now in this case, I had conditions, right? If A of mid is equals to key, my end becomes mid, right? Else, if A of mid is A of mid is less than key, right? A of mid is less than key, that means key is greater. So I have to start looking into the right hand part, right? Else I had to start looking into the left hand part. Yeah, good. So we'll dry run this code here, right? So let's start. What will be the mid to start with? Mid will be, as we know, right? S plus E minus S by 2. For small integers, you can just do S plus E divided by 2. But this particular condition is for big numbers, like not to overflow. But small number, it's equivalent to 0 plus 7 divided by 2, which is 3.
3.
Right? Now, which condition out of these 3 hits? I'm looking for key, by the way, 3. Which condition out of these 3 hits?
First one.
The first one, right? That means my end becomes here, my start is still here, right? I can safely discard this. Got it?
Yes.
Now I come again, is S less than or equals to end?
Yes.
Yeah, S is less than equals to end. Yes, we come on a while loop. We do the mid again. What will the mid now? Your end is
2.
3, your 0 is S is 0. So what will be the mid?
2.
Now 0 plus 3 divided by 2 is 1, right?
Yeah, I mean to say position 1.
Position 1, element 2. Yeah.
Correct.
So this is mid, right? Which condition will hit?
Second one.
This one, right? A of mid is less than key. So your start will become S plus, mid plus 1, which is this. So now this is discarded, right? Now what will happen? S plus E divided by 2. What is the mid?
2. I mean like the index 2.
Index 2, right? So now which condition hits?
First one.
First one. So end becomes here.
And will be also 2.
Yeah. So now you remember we had this while condition which said S is less than or equals to end, and then everything works, right? This was the condition, right? So in this case, does that condition satisfy? S is less than equals to E?
Yes, it
Yes,
satisfies.
right? You go inside the while loop, right? In this case, what will happen? Mid will be again what? 2 plus 2 divided by 2 is 2. Which condition will hit? The first one, right? A of mid is equals to key, right?
Correct.
Again, end will become mid, right? So nothing changes there. S and E remains the same. You go into the while loop. S is less than equals to E. Yes, you again go it. Mid is again 2. You again come back. While S is less than equals to E. Yes, again go down. So you go into the infinite loop. Got it?
Correct.
This is what I want to explain you, right? Since we are going into infinite loop, we need to break it at certain point of time, right? So what we'll do is, instead of going till the last element, I will stop this when there is only one element. In that case, I will stop when S is equals to E, right? So I will just run a while loop while S is less than E. That's all I do, right? And then if you look at this, right? It will exit when this particular 3 is remaining, right? While loop will finish, right? But if I finish the while loop when there is still one element left in the array to be tested, right? I have to test it specifically, right? Because it didn't cover in the while loop. If I cover it in a while loop, I go in infinite loop. So I stop it when there was only one element. So I had to test it at the end. What I have to test is if my a of s is equals to key, right? Then I return the mid. If that is not the case, if the last element which is left on the array is not the key, then I return -1, right? That's the last specific case I am handling, right? Because if I do in a vanilla flavor binary search, it will just go infinite loop. That's why I stop one element before, and then I do a specific case on one element, right? I handle the specific case of one element array, which is if a of s is equals to key, then sorry, not mid, sorry, this is s. Yeah, I return the start index. If it is not the key, I'll return -1, right? That's the specific case. Everything else is covered in the while loop. In vanilla, we didn't need that specific case because we are not going into the infinite loop there, right? And I tell you a rule of thumb, right? A lot of people get confused. Hey, when to do s less than e and when to do s less than equals to e, because in vanilla flavor we did this. In this question we did s is less than equals to e, right? So when to do that and when to do the other one is very small trick. If you are returning from within the while loop, then it should always be s less than equals to e, because at certain point of time that return will actually break the loop, right? So you don't have to actually explicitly break the loop and come and do the whole testing here. But if you are not returning from the while loop, you have to do s is less than e, and you have to do a specific case for one element here. In binary search, that's the most confusing piece. S less than equals to e or s less than e. Rule of thumb, if you're returning from while loop, right, s less than equals to e. If you're not returning from while loop, s less than e. That's it. Did you get the understanding of this particular first instance, how to find first instance of an element? Any
Yeah,
doubt
I
before?
understand. Yeah, I understood, but I still didn't understand how would it identify the first instance?
We ran
Like
it,
how
right?
does it know that? No, in the dry run, this works, but how are we ensuring that this is the first three?
That's what we are ensuring, right? Till the time we don't get, like, till the time we are getting 3, we are going further and further, right? On the left, the whole code is to ensure that this is the first instance, right? The what, like, how can I say, like, this code works by testing it, right? And we ran the
Got it.
code.
So what you're saying is when we were doing the vanilla, in as soon as it was equal, we were returning out. Now
Yes,
we are not doing it. We will keep going until we keep finding and s is less than e, so
yes.
that we get to a stage where it is the first element, and then after we come out and the outside if will handle the returning of that first instance.
Yeah, if there was an instance, right? If you can say, like, hey, this array was 1 2 3 3 3 4 5 7, and I want the first instance of, like, 6, then it will return null, right? A -1, right? So
Yep, got it.
so this is to check if there was only one element, is that the element key? If yes, then we'll return that instance. If not, then we'll return -1. This is s is less than e is not to find the first instance. This is to find the first instance. In earlier version, what we were doing,
We were returning here.
we were returning here. Here, what we are
Right.
doing is we are squeezing the array, right? And going into the left-hand side and finding if there is more like this, right? So you go left, left, left till the time you find more, more, more. So when you don't find more, that means that is the first array, right? First instance, right?
Got it.
So it's not that first instance, first mid you found as a key, you return it. Then it will be a vanilla binary search. But since you are squeezing the array and you're going to the left hand side, hey, maybe there is more instances before it. So they will be the first instance. Okay, there is more instances and then more instances till the time you find the leftmost instance, and that will be the first instance, right? You run it, dry run this code for 5 times, right? For different cases, and then you'll see like how it works, right? So code is very simple. I think I almost wrote the code. It's a while of s is less than e, mid, find the mid, do these 3 conditions, and then at the end just return this, right? So this is the first instance of in an array. Any doubt, guys? Any other questions before I move?
I have 2 questions here. So first question is, if this was a last instance, then we cannot use binary search, right? Like the same question was that we have to find the first last instance of that particular
Why do
thing.
you say that?
Because we are always going towards the left side, right?
But like, okay, so you can't use the first instance code for last instance, right? But do you mean to say like you can't use the binary search approach for the last instance? Or you want this code to work for last instance? The code is different, right? You getting my point?
Yeah, getting. So it's basically like, how would we make it? So right now this is moving towards left always, right?
Yeah.
You get the mid, then you try to get that particular thing again into that mid of mid, right? So how do we make sure that it moves towards the left? Because if you had 3, let's say if this example you had 3 after 3 also, how
Mhm.
would you make it move towards left? Because greater than 3 is not still there, right? It is less, it is equal to 3, so it has to move towards left or right. How would it know?
Look at this. Look at the code, right? Look at this condition, right? Where this condition executes, right? This condition is a of mid equals to key, right? Then it moves to the left because end becomes mid. There is another condition which is this. Right? It also moves the end to mid -1. That means you are moving to the left, right?
Right.
So give me an example where you think that it will not move.
So if
Let's
you
run
had
it.
3 3 3, yeah.
Where?
If
Where?
you have 3 after 4th
Give me the
position,
full array. 1, 2, 2,
1
1,
2
2.
3 3 3 and one more 3 and
Hmm.
4 5 7.
Yeah.
So
So
in
what will
this
be the mid?
scenario, 3, the 4th position.
This is 3. Yeah. So
Correct.
which condition will hit?
First one.
So your end becomes here. Your
Yes.
start is here. Yeah.
Correct. Right.
So now what will be the mid?
Mid will again be between the 2. So this will become the first instance.
Which one become the first instance?
No, like it's going towards the first. I'm saying that if I have to make it move towards the right side to
Yeah,
get the
then
last instance of 3.
yeah, so like wait. We can't make a code which is written from first instance to work for last instance. Yeah, we have to write new code. Yeah, you're like, you want a code which is written for first instance to work for last instance. That's not reality, right? I have to write another code for that, right? So you're getting the point where what we are trying to do here is like, I have written the code for first instance, right? And you want it to work for last instance. How can that be happening? Right? You have to
Right.
write
No,
another
I'm
code.
not saying that same code, but will binary search work for a last instance?
That's what the first point I made. Like, do you mean the code or do you mean the algorithm? Algorithm will work,
The
and that is
algorithm.
the next question I'm taking. right? That's
Okay,
the
got it.
exact next question I'm taking. The last instance of an element, right? It will work, right?
Got it.
There will be some changes in the code. More or less code remains the same, but there will be some code where you will move to the right hand side rather than the left hand side. That was your question, right?
Yes, right.
Okay, so what was your other questions? You said two.
Yeah, the second question is that by looking at this question, right, as such, how do we identify that this has to go to a binary search algorithm? Like, are there any tricks of it?
The
Like,
first
just think
sentence,
it this way that we have done so many different algorithms, and now this question comes. How do we first, just looking at the question, identify that this
so
should be a
if
binary search?
if you listen to my first sentence, right, when I started this problem, was, hey, this is an assorted array, right? And then I said like, hey, if there is a sorted array, just give a try to binary search, right? I'm not saying that there's 100% of the time that will work, but 99.9% it will work. If it is a sorted array, think of binary search, right? Anything sorted, think of binary search, right? That's why it is sorted. Take the advantage of sorted nature of the input, right? And then apply the binary search. So that was my first set. I cover a lot of things fast, so please pay attention to every sentence I say. If you miss, please ask me to repeat. I'm okay to that, but anything I say has some value to it, right? So please be very attentive to, and I move very fast because my this class is more for FANG, right? So I assume a lot of things. So if you don't know that thing, please let me know. I'll explain it in detail, right?
Got it. Okay. Thank you.
So yeah, if you see an input array which is sorted, think of binary search, right? Cool. So let's go to the next problem, which is what we already have discussed, is last instance. Right? So let's go again to the example which we were working with. 1, 2, 3, 3, 3, 3, right? And 4, 5, 7. And we want to find the last instance of this array, right? The step number 1, write the indexes on the top of the array. It makes our life easy, right? What is the mid of this array? The start is this, end is this, right? Now key I'm looking for is 3. So I'm finding the last instance of 3, right? Now, what this is, a of mid is equals to key, right? What does that tell me, right? In the first instance, I knew that, hey, this may or may not be the first instance because it is equals to the key I'm looking for, but it may not be the first instance. The same doubt I have when I have the last instance. This is equals to the key, but this may not be the last instance. Where would be the last instance? For first instance, it was on the left hand side, because if there is a first instance of 3, it has to be before it, which is the left index, left part. If there has to be a last index of the 3, where it had to be? It has to be on the right hand side, right? So if in previous case, when a of mid was equals to key, we did end equals to mid. In this case, we'll do s equals to mid, right? So you will search in the last index in this case, right? Very simple turn of events, right? Now, if a of mid is less than key, so that means the key is greater than the mid. That means, again, you have to look into the right hand part. Else, if a of mid is greater than key, then you have to look into the right hand, left hand part, right? So that's it. That's the last instance, right? There is a small trick where this particular code breaks, and let's write the code, do the dry run, and identify where it breaks, and then let's fix it, right? And then of course we will stop when there is only one element, and then at the end we'll just check if that is equal to the key, we return the index, and if not, we'll return the -1, right? But did you get this, the algorithms piece, how it will move to right now? Earlier it was moving to left because we were setting e equals to mid. Now we are moving to right because that's why we are setting s equals to mid. Following me? Any doubt before I move and write the code?
Yeah, I'm clear. Thank you.
Guys, no sounds from other guys. Are you guys listening or?
Yes, we are
Hey,
listening.
Yeah,
okay,
we are listening. Yeah.
okay. Please raise your doubts. If I'm moving fast, slow, anything, not understanding. Good stuff. So let's write very quickly the code. Last instance, right? This is A. This is key, right? So what will we do? We'll do integer s equals to 0. Like this is the typical template of binary search, these 5 lines, right? While s is less than e, mid equals to s plus e minus s divided by 2. If a of mid was equals to key, then your start becomes mid, right? Because we are looking into the right hand side. Else if a of mid is greater than, sorry, less than key, then also start equals to mid plus 1. Yeah, else you become end equals to mid minus 1. That is left hand part. And then if, sorry, let's use a tertiary, return if a of end or s, whatever you want, right, is equals to key, then return end, else return -1. That's it. This is a tertiary operation in Java. Actually, it should be same in Python as well, right? I don't know. You write tertiary operation like this in Python?
No.
Yeah.
I will just
Oh,
write
yeah.
this e equal to -1. That one is possible, but this I didn't understand the question mark.
So this is like, this is equivalent of if a of e is equals to key, return e, else return -1.
Oh, it's like you're writing a list comprehension.
No, it's a very simple. It's a, like, just write if else. Like if in Python you can just write if else, right? If the last element is equals to key, return the last element index. Otherwise, return -1. That's the whole idea of writing this code. I think it's the same in Python as well. Like search. Yeah. Anyhow, so. Let's run this code, right? We wrote it, we understood it from the previous example, we wrote it. Let's write and then see like if this code works actually on an input. So let's take, right, and okay, what will be the mid? This will be the mid, right? And I'm searching for key equals to 3, right? So what will happen? S is less than E, yes. Mid is equals to 3, index 3, right? A of mid is greater equals to key, yes. So S will start becoming the mid. So my start is now here, my end is here, right? Now again I come back, right? S is here, E is here, I take the mid. Mid is 3 plus 7 divided by 2, which is this one, right? Again, this condition hits because A of mid is equals to key, great. So my S becomes here, right? I come here, I again do the mid. What is mid? 5 plus 7 divided by 2, which is 6. This is mid my, right? Now this condition is not true because A of mid is not equals to key. So I go here, A of mid is less than key? No, because it's greater than key, actually it's 4, right? So I come here, end becomes mid minus 1. So you come here, your end becomes mid minus 1. So end is here now. S and E are, so you finish the loop, you come back, and then you say like, hey, is A of E equals to key, which is correct because this was the E, right? Then you return the index, which is 5, right? That means if you look at, this was the last index of the 3, right? Got it? Now, what if I told you like there is a mistake in this code? It worked, right? In our dry run case. But what if I say like it will go into infinite loop at certain point of time? How would you feel? And how would you will be more confused, like how would I figure that out? If it works for my dry run case, how would I figure out that this will not work for other cases, right? Or any binary search implementation, how can you be sure that this code will work for any other case, even though you tested it on a dry case, right? And that is where the trick comes in, right? Trick is very simple, right? Always test your implementation for 3 test cases: empty array, 1 element array, 2 element array, right? When you are finding for last instance, first instance, always look for the first instance of 2, last instance of 2 and last instance of 1. In this case, last instance of 1, and then in this case, a last instance of anything, right? It should return you -1. So let's try this case number 1. It's an empty array, E equals to -1. You come here, S is 0. Is it less than -1? No. You come here, you try to access this A of E, which is
Index error.
index error, because A of -1 is wrong. So this code doesn't work for empty array, and this is where Prabhay you told, right? This is where we had to put a condition. If it is less than, not equals to 0, just return, because then there is no point doing all those things, right? Otherwise you will end up accessing the end array here. So then you will be array out of bound, index error, right? Good. So we covered that. So now our code will work for empty array, right? Great. Now let's test it for 1 element array, right? So what will be the 1 element array? Let's say I'm finding for the last instance of 1. So what will happen? S is 0, E is 0. Great. A of length is not equal to 0, so I don't return. S is 0, E is 0. So while loop doesn't enter because S is not less than E. Understood? Because S is 0, E is 0. So while loop doesn't get entered. We come to the last return statement, and let's say key was 1, right? So A of 0 is equals to 1. Yes. So I return 0, which is end index, and that works for it. But I want to test it for a last instance of 2. The same test case, I want to check for an element which is not existing in this, right? Because that will give me the confidence that if the number doesn't exist, it also returns me -1, right? So again, we go here, S is 0, E is 0, while loop doesn't enter, return A of 0 is equals to 2. No, so I return -1. It works. This case works. Great. Now let's start with third case, right? So in the third case, what will happen? 1, 2, right? And here S is 0, E is 1, because 2 minus 1, right? The while loop executes, and I'm looking for last instance of 1, let's say, right? I'm looking for last instance of 1. What will happen? S is less than E, great. Mid equals to S plus E minus S by 2, which is 0 plus 1 divided by 2, which is 0, right? So my mid is now 0. Now, is this condition true? A of mid, is this true? A of mid is 1. Your key is also 1. Is this condition true?
Yes.
Yes, right? So what will happen to S? S will become 0 again because mid is 0, right? You come here, again, S is less than E, right? Because it's 0, it's 1. Again, you come here, 0 plus 1 divided by 2, again 0. Again, come here, S equals to 0. Again, go here, you go into infinite loop. That means this code doesn't work for this case. Right? See, like I found like 3 important test cases and I ran it and I figured out 2 different problems, actually 3 different problems in this code. Right? So that's the beauty of doing dry run on a smaller test cases. It worked for the perfectly worked for the other bigger test case, right? But when you look at the edge cases, these are the smaller test cases which help you a lot. These are the 3 standard test cases, right? Which you should always look, right? Whenever you are dealing with a binary search problem, that will give you a lot of your edge cases. Like if you have to test a dot length equals to 0, if you have to if you are going an infinite loop, anything, right? It will quickly give you, which bigger test cases will not give you, right? Or it will take some time to actually execute them. This is like one element quickly, right? So that was the trick I wanted to show you, like how to identify the problems in your code by running these 3 test cases. Okay, now we found the problem. How do we fix it, right? And this is where I want to tell you is, whenever you are stuck in S not moving ahead, right? Whenever you are stuck, when the start doesn't move ahead, and then that's why you are stuck in an infinite loop, always try to odd it out, right? The mid should be ordered out, because if you're this means there are even number of element, and that is why S is not moving, right? So if you make it odd, it will start moving, and then you will run out of the you will get out of this loop, right? So always do, if you run a dry run and if you find that your start is not moving, that's why you're going an infinite loop, go to the mid statement and then just do this S plus E, sorry, S plus E minus S plus 1 divided by 2, right? So in this case, what will happen? Let's run it. S is 0, E is 1. Yeah, E is 1. So less than, you come here. Yeah. 0 plus 1 minus 0 plus 1 divided by 2. So your mid is now 1, right? You say like, hey, is A of mid equals to key? No, because I'm looking for 1 and it's 2. You come here, is A of mid less than key? No, because I'm looking for 1 and A of mid is 2. So your end becomes mid minus 1, right? So your end is here, your start is here, right? Again, you come here, right? S is less than E? No, because both of them are same. You come here, is A of E equals to 1? Yes, so you return 1. Oh, sorry, index 0, right? That's it. You actually solve the case, right? So the crux of this entire explanation was not that you have to do an odd one, that's a trick, right? But important is, how do you identify your edge cases with these 3 test cases, and how do you fix your code which you have written with dry running the code as using these 3 test cases. Any doubt on this?
So when you added +1, will the second case work?
Yeah, try it. Try it. Take your time and tell me if it will work or not. Second case, we never entered into the while loop, if you remember. So it doesn't matter for that,
Okay, got it.
right?
Got it.
So there are few takeaways from this class. The first takeaway is when to do S less than E and when to do S less than equals to E. If you are returning from while loop, S less than equals to E. If you're not, S less than E. If you look at this code as well, we are not returning, so S less than E. How to make sure that your code works for binary search? If it is based on out of binary search implementation, how do you make sure that all the edge cases are covered? Run these 3 test cases, right? One empty array, 1 element array, and 2 element array. If it works for these 3 test cases, it works for every test case. You don't have to test any other 2 case, right? So these are the 2 big takeaways from this class in binary search, right? Another last problem which someone also already hinted at is finding the number of instances. If there are duplicate numbers, finding the number of instances of that duplicate number. Do I need to tell you like how would it work? If you know the first instance, if you know the last instance, can you find the number of instances?
Yes, it's
Yeah.
possible.
And it will be having a time complexity of log of n, which I'll cover in the time complexity class, but remember this log of n, right? That's about it. That's the first dose of a binary search, right? Just go through the vanilla binary search, write down the code for these 3 problems. Tomorrow the problems will be on rotated sorted array. Again, binary search, but the array will be sorted and rotated, right? So similar kind of codes will be written. You will be fed up of while loops and s is less than e less than equals to e, right? For tomorrow as well, or the next class as well, right? But that will concretize your binary search algorithm, because that's the class of problems which are asked from binary search. Yeah.
But आपने बोला, sir, you said that like to find a number of duplicates, the time complexity would be n
Log of n.
log of it would be n log of n, right? So
Why?
because like I need to first iterate on the array, and then I need to write another algorithm to search for it, whether it exists or not, right?
Why? Why would it be n log n? So how do you find number of instances? Let's start with there.
Okay.
How do you start? How do you, like, if I tell you uh, how many red balls are there in this line, right? Let's start there,
Uh,
right? What you'll do is, like, you find the index of the last red ball, right? Which you can do it in log n. Let's say you have an algorithm which you can find it in log n, right?
Yeah, I think let me phrase my question. So my question was like not just finding all duplicates for one number. I was basically saying that, okay, let's say we have an array, 1 1 2 2 3 3 4 4 5 5 and 6. So basically I would like to know uh, in array, like basically it would be the number which are more than one actually. Tell me all the numbers which are more than one, like duplicates number, not just one.
Okay. So this is a different question actually,
Yeah, yeah.
right? Then yeah,
That's why I was thinking that it would be like L log n, because you don't know, right? Which all numbers are having an occurrence more than one.
yes, that's true actually. It can, this particular algorithm can be used for that as well, right? But I am not sure like it will be beneficial, because if it is n log n, even sorting will work, right?
That's true.
Yeah, and if the array is already sorted, right, all you need to do is you can find it in O of n time actually. You don't need to do this n log n even, right? Then it's overkill. So what you need to do is, like, till the time the number is equal to the previous one, you count plus plus, right?
Yeah, yeah.
Yeah. If it is a sorted array, you don't need to do a this whole thing to find that, because that will mean, you know, additional complexity. Here we have to first search it and then find the instance. That's why it's more efficient in that terms. But in the other example, you don't even need to find it, you need it for everyone, right? So
That's
like, yeah, that's O of n actually. If you apply this, it will be O of n log n, right? So let's say if you had this, right, you just take this number, right, and then move forward, right? If this number is equals to the previous number, you tell, hey, there is one number which has count more than one. If not, you just keep the count equals to 0, right? Then you move here. If this number is equals to this number, then there is at least one number which is more than that, and then you move forward, right? Then this number, till the time you get the end of this, you keep the count, right? And then you
Yeah.
move this, then you move this, and then you move this. So this is linear algorithm O of n if it is sorted array, and you have to find it for all of them. If you have to find one of them, then it's log of n,
Yep. Understood.
right? So yeah, it's not that you have to apply it everywhere, right?
So here, when we do the first instance, it will be log of n, and the second instance also log of n. So in that scenario, won't it become 2 log n?
No, sorry, we are not applying that log of n here, right? Because
No, no,
it's
not here, not here. Like counting. So let's say if I had to do count of 4 here,
Mhm,
specifically 4, then first we will do find the first instance,
mhm,
then we will find the last instance,
mhm.
right? So whatever logic we applied for first instance, we will apply that. Then we will apply again with the last instance.
Yep.
So the same loop will the while loop will be, there will be 2 while loops, right, in that code.
Yep.
So won't that be 2 times log n?
Yep. So that's the fundamentals of time complexity, right? You don't
So
care about
I'm just
constants.
asking that that 2 does not correspond to n log n, or
No,
it is like we
no,
remove it.
no. So the fundamentals of time complexity, right? I don't want to cover that here. I will cover it in a separate class. Fundamentals of time complexity is that you don't care about constants. If it is not proportional to the input, right? In this case, 2 is not proportional to the input, right? The n can be a billion, still you'll run it to 2 multiplied by log n, right? And n
Okay,
can be equals to 1, and still you'll be running 2 multiplied by log of n, right? So there is no relationship between the input size and the number. That's why you drop it, right?
got it.
So yeah, if it is proportional to like n, the input size, then you keep it. If it is not proportional, then it's more of, even if it is a million, even if it is 10 million, if it is a billion, if it is not depending on the input, you can drop it because that's constant, right? If it is, in this case, it was 2, it was easy to drop it. But if it was a million times log of n, and it is not proportional to the input size, I will still drop it. It will be still log of n, right? So
Got it.
yeah, it's a constant thing. It's a fundamentals of time complexity. I will cover there.